The James Webb Space Telescope turned its infrared gaze toward a visitor from beyond the solar boundary. What it captured was not the diffuse halo expected around a distant nucleus. Instead, JWST's sensors recorded something more structured, a persistent emission layer wrapping the core with unsettling uniformity. The signal did not fade at the expected distance. It did not diffuse as gas and dust should. Its spectral signature remained stable across multiple observation windows, unresponsive to the changing intensity of solar radiation. The boundary between this layer and the surrounding void appeared sharper than physics typically allows. For 3 consecutive observation cycles, the emission remained locked in place, as if tethered to the nucleus by something other than thermal pressure. One interpretation suggests a transient interaction between exotic volatiles and the solar wind, a rare but explainable phenomenon. But if that surface is not passive, if it is responding to external input in ways that suggest regulation rather than reaction, then 3I Atlas is not simply crossing our system. It is carrying something we have not encountered before. On the night sky's canvas, among the fixed choreography of planets and the predictable arcs of known comets, occasional visitors arrive unannounced. They carry with them the chemistry of distant stellar nurseries, the gravitational echoes of systems we will never reach, and sometimes, very rarely, behaviors that resist immediate categorization. 3I Atlas entered our telescopic record as a faint smudge on automated sky surveys, unremarkable at first glance. Its brightness curve suggested ice. Its motion suggested momentum inherited from interstellar space. But within weeks of confirmation, something about this object began to diverge from the expected script. The discovery itself followed routine protocol. On a crisp autumn night in late 2023, the Atlas survey system flagged a transient near the plane of the ecliptic. Initial positional measurements placed it inbound, approaching from the direction of the constellation Lyra. The object moved swiftly, too swiftly for a long-period comet bound to our sun's gravity. Follow-up observations confirmed what the preliminary data suggested: hyperbolic trajectory, eccentricity greater than 1, velocity components inconsistent with solar escape from the Oort cloud. This was not a piece of our system returning home. It was something passing through, its origin rooted in the space between stars. Orbital reconstruction painted a precise picture. The object's inbound velocity measured approximately 34 kilometers per second relative to the sun's rest frame, placing it firmly within the interstellar velocity distribution observed in our local neighborhood. Its trajectory, when traced backward, did not converge on any known stellar system within 50 light-years. It simply emerged from the galactic disk, following a path shaped by ancient encounters we could only infer. At the time of discovery, 3I Atlas was roughly 4 astronomical units from the Sun, beyond Mars, inbound toward the inner system, brightening slowly as solar flux increased. This made it the 3rd confirmed interstellar object detected passing through our solar system, following ññnWhen in 2017 and Totiwai Borisov in 2019. Oumuamua had been a puzzle wrapped in ambiguity, elongated, tumbling, reflecting light in ways that defied clean interpretation, exhibiting non-gravitational acceleration with no visible outgassing. Borisov, by contrast, had been comfortingly ordinary, a classical comet with a bright coma, a visible tail, and spectroscopic signatures matching known volatile ices. It behaved as theory predicted, offering reassurance that most interstellar visitors conform to familiar physics. 3I Atlas occupied uncertain ground between these 2 precedents. It displayed coma activity, faint but detectable, suggesting the presence of sublimating ices. Yet its brightness evolution did not track cleanly with heliocentric distance. Standard models predicted a steady increase in luminosity as the object warmed, driven by accelerating sublimation rates. What observers recorded instead was a stepwise progression, with plateau regions where brightness held nearly constant despite continued solar approach. Photometric monitoring revealed subtle periodicities in the light curve, hinting at rotation or surface heterogeneity, but the amplitude and phase behavior resisted simple geometric interpretation. By early 2024, as 3I Atlas crossed inside 3 astronomical units, global observing campaigns were underway. Ground-based facilities across 6 continents coordinated timing windows. Space-based assets reallocated observing schedules. The goal was not merely to characterize another interstellar comet, but to understand whether this object's peculiarities represented rare but mundane physics, or something requiring deeper reconsideration of what arrives from beyond our stellar boundary. Then JWST acquired its first deep infrared dataset, and the narrative shifted. The near-infrared camera captured the nucleus in unprecedented detail, resolving structure at scales no ground-based telescope could achieve. What appeared immediately in the processed images was a central point source surrounded by an extended emission region. This was expected. Cometary nuclei emit dust and gas. Instruments detect that emission as a diffuse envelope. But the morphology here was atypical. The boundary between the nucleus and the surrounding glow was not gradual. It was defined, almost discrete, forming a shell-like structure with radial symmetry that persisted across multiple observation epochs. Spectroscopic follow-up revealed the next anomaly. The emission spectrum within this boundary layer showed features consistent with thermal radiation, but the temperature profile did not match the expected gradient for sublimating ices exposed to solar heating. Surface temperatures derived from mid-infrared observations suggested a cooler nucleus than models predicted for an object at this heliocentric distance. Yet the boundary layer itself radiated with a brightness temperature slightly elevated above equilibrium, as if energy were being redistributed or retained in ways that classical thermal models did not anticipate. The Hubble Space Telescope contributed complementary data in the ultraviolet and visible bands. High-resolution imaging confirmed the presence of the boundary structure, now visible as a faint but persistent halo in reflected sunlight. Crucially, the halo's brightness did not fluctuate in phase with the nucleus's rotational period. If the emission were purely tied to localized surface features, active vents, or exposed ice patches rotating into sunlight, brightness variations should have mirrored the spin. They did not. The layer appeared stable, uniform, detached from the nucleus's rotation, in a manner that suggested either a surrounding cloud of particulates with anomalously low velocity dispersion, or a surface interaction process acting continuously around the entire nucleus. Ground-based spectroscopy from the European Southern Observatory's Very Large Telescope added further detail. High-resolution spectra revealed weak emission lines consistent with ionized gas, sodium, iron, possibly magnesium, concentrated within the boundary layer. These metallic species are common in cometary comae, typically liberated from dust grains by solar photons. But their spatial distribution here was unusual. Rather than dispersing radially outward in the expected fountain pattern driven by radiation pressure and gas drag, the ionized metals appeared confined, their emission intensity dropping sharply beyond the boundary layer's outer edge. Radio observations from the Atacama Large Millimeter Array probed the object's molecular inventory. ALMA detected carbon monoxide, water vapor, and tentative signatures of more complex organics, all standard cometary volatiles. But the gas production rate, derived from molecular line intensities, was lower than expected given the object's brightness and heliocentric distance. There was a discrepancy. The amount of light scattered and emitted by the boundary layer exceeded what the measured gas output could plausibly generate through standard dust entrainment and sublimation processes. Amateur astronomer networks contributed light curve data spanning weeks, capturing photometric behavior at temporal resolutions unavailable to professional observatories operating on tight schedules. These datasets revealed microvariations, flickering on timescales of minutes to hours, superimposed on the broader rotational modulation. The microvariations lacked obvious periodicity, but were statistically significant above measurement noise. They resembled the stochastic brightness fluctuations, sometimes seen in active comets during outburst events, yet Atlas showed no evidence of discrete outbursts in its overall activity profile. Observers compared notes. The emerging picture was one of consistency across platforms, wavelengths, and observing geometries. The boundary layer was real, repeatable, and present in datasets collected by independent instruments on different continents and in different orbital regimes. It was not an artifact of image processing. not a trick of scattered light, not a calibration error unique to one facility. Whatever physical process was generating this structure, it was intrinsic to the object. To understand why this mattered, it helps to establish what normally happens when a comet approaches the Sun. A cometary nucleus is a small, irregular body composed of dust, rock, and frozen volatiles. Water ice primarily, along with carbon dioxide, methane, ammonia, and trace organics. As the comet enters the inner solar system and solar flux increases, surface ices begin to sublimate. Gas molecules escape the nucleus, carrying in train dust grains with them. This outflowing mixture forms the coma, a diffuse atmosphere that can extend tens of thousands of kilometers from the nucleus. The coma's structure is governed by well-understood physics. Gas velocities depend on the sublimation rate, which in turn depends on temperature, which depends on heliocentric distance and surface albedo. Dust grains decouple from the gas flow once gas density drops sufficiently, then follow ballistic trajectories shaped by solar radiation pressure. The resulting envelope is roughly spherical near the nucleus, but becomes asymmetric farther out as radiation pressure pushes dust into a tail aligned opposite the Sun. Spectroscopic observations of the coma reveal molecular emissions, atomic lines, and dust continuum. These signatures allow observers to infer composition, temperature, gas production rates, and dust-to-gas ratios. Standard models predict how these parameters scale with heliocentric distance. Brightness should increase as the comet approaches the Sun, following power law relationships calibrated from decades of observations. Coma density should peak near the nucleus and decline smoothly with distance, according to radial outflow models. Dust tails should brighten and lengthen as production rates rise. Non-gravitational forces, caused by asymmetric outgassing, acting like tiny rocket thrusters, should produce measurable deviations from purely Keplerian orbits, detectable as small accelerations in the object's trajectory. For most comets, these models work. Observations align with predictions. Deviations, when they occur, are usually minor and attributable to surface heterogeneity, seasonal effects as different hemispheres rotate into sunlight, or discrete outburst events triggered by subsurface pressure buildup. The physics is messy in detail but predictable in aggregate. Comets behave like dirty snowballs heated by a distant furnace, complex, dynamic, but ultimately comprehensible within the framework of classical thermodynamics and gas dynamics. 3a. Atlas did not follow this script cleanly. The first anomaly was spectral rigidity. Cometary emission spectra typically vary with heliocentric distance as temperature changes and different volatiles reach their sublimation threshold. Water dominates beyond 2 astronomical units. Carbon dioxide takes over farther out. Exotic ices like carbon monoxide sublimate at even greater distances. As the comet moves inward, the spectrum should evolve, reflecting the changing composition of the outgassing mix. For 3i, Atlas, the evolution was muted. Spectra taken weeks apart, spanning a range of heliocentric distances, showed minimal variation in relative line strengths. The boundary layer's emission profile remained stable, as if the source region were buffered against changing solar input. The second anomaly was brightness decoupling. Photometric models predicted a brightness increase of roughly 40% as the object moved from 4 to 3 astronomical units. Observed brightness increased by only 20%. The shortfall was not explained by geometry or phase angle effects. It suggested either that the albedo was changing, surface properties evolving in response to warming, or that the emission mechanism was not purely driven by sublimation. If the boundary layer's brightness depended on some process other than direct solar heating, then standard photometric scaling laws would not apply. The third anomaly involved non-gravitational acceleration. When precise astrometry was used to refine the orbit, analysts detected a small but persistent deviation from the expected trajectory. This by itself was unremarkable. Most active comets experience non-gravitational forces. What was unusual was the direction. Standard cometary jets produce acceleration vectors biased toward the sun-facing hemisphere, creating outward thrust. The acceleration detected for 3e, Atlas, had a transverse component inconsistent with simple sunward outgassing. The magnitude was also smaller than expected given the observed coma brightness, suggesting either inefficient momentum coupling or that the visible emission was not the primary source of the force. The fourth anomaly concerned the dust tail alignment. Cometary dust tails curve gently as they trail behind the nucleus, shaped by radiation pressure and the comet's orbital motion. The curvature and orientation depend on particle size distribution and ejection velocities. Observations of 3 Atlas revealed a tail present but faint, with an orientation slightly misaligned from the predicted anti-solar direction. The offset was subtle, within margins that could be attributed to large, slowly moving grains. But when combined with the low gas production rates, it suggested that either the dust was unusually massive, or that the ejection velocities were lower than typical for the observed brightness. The fifth anomaly was thermal inertia. Infrared observations allowed estimation of the nucleus's thermal properties, how quickly it heated and cooled in response to changing solar flux. High thermal inertia materials like rock heat slowly and retain heat well. Low thermal inertia materials like porous ice respond quickly to temperature changes. The derived thermal inertia for 3I Atlas was intermediate, neither clearly icy nor clearly rocky, and appeared to vary depending on which region of the boundary layer was analyzed. This suggested either a compositionally heterogeneous surface or a multi-layered structure with different materials at different depths. Individually, each anomaly could be explained. Spectral stability might reflect unusual composition, perhaps refractory organics with high sublimation temperatures forming a lag deposit that insulates underlying ices. Brightness decoupling might result from changing albedo as surface texture evolves under solar heating. Non-gravitational acceleration might come from localized jets, not resolved in imaging. Tail misalignment might be a transient effect of recent outburst activity. Thermal inertia variation might indicate patchy surface coverage of different materials. But taken together, the anomalies formed a pattern. They suggested that the boundary layer was not simply a passive coma produced by straightforward sublimation. It behaved as if regulated, as if energy input, particle ejection, and thermal response were being moderated by some mechanism beyond the simple interplay of solar heating and ice vaporization. One hypothesis invoked exotic volatiles. Perhaps 3 Atlas carried ices unknown or rare in solar system comets. Complex organics with unusual sublimation curves, or clathrate hydrates that trap volatile molecules within crystalline water ice cages, releasing them gradually as the structure destabilizes. Such materials could produce emission profiles decoupled from heliocentric distance, if their sublimation kinetics depended on factors other than temperature alone. Internal pressure, crystal phase transitions, or radiation chemistry driven by cosmic rays accumulated during interstellar transit. Another hypothesis considered fractal dust aggregates. If the dust grains ejected from the nucleus were not compact particles but fluffy, low-density aggregates with fractal structures, their optical properties would differ dramatically from standard models. Fractal grains scatter light more efficiently per unit mass, potentially explaining the brightness excess. They also have larger surface area to mass ratios, which could enhance their interaction with the solar wind and radiation pressure, creating the observed non-gravitational forces and tail misalignment. A third hypothesis focused on plasma interactions. Cometary comae are not electrically neutral. Solar ultraviolet light ionizes gas molecules, creating a tenuous plasma that interacts with the solar wind's magnetic field. Under certain conditions, this interaction can generate extended structures, ion tails, plasma boundaries, even bow shocks if the gas production rate is high enough. Perhaps the boundary layer around 3 Atlas was a plasma phenomenon, a region where ionized gas, trapped by magnetic fields or electrostatic forces, formed a quasi-stable envelope around the nucleus. This would explain the metallic emission lines and the layer's apparent detachment from surface rotation. A fourth hypothesis explored surface self-organization. Some planetary surfaces exhibit patterning, dune fields, polygonal cracks, sorted stone circles, generated by feedback loops in physical processes like thermal cycling, wind erosion, or freeze-thaw dynamics. Could the boundary layer represent a self-organized structure formed by cyclic sublimation and redeposition, where ejected material falls back onto the nucleus in patterns that enhance or suppress further sublimation, creating stable spatial patterns. In emission, laboratory experiments with sublimating ices under vacuum have produced dendritic and cellular structures. Perhaps something analogous was occurring here at macroscopic scales. A fifth, more speculative hypothesis invoked swarm dynamics. If the nucleus were shedding not just gas and fine dust, but also larger particulates, pebbles, ice chunks, or aggregates, these could form a gravitationally unbound, but dynamically coherent, swarm orbiting the nucleus at low relative velocities. Such a swarm would scatter sunlight, creating an extended halo. If the particles were large enough to have significant thermal inertia, they would emit infrared radiation with a temperature profile distinct from the nucleus surface. The swarm's collective optical signature could mimic a boundary layer, especially if particle ejection were continuous and velocities low enough to keep the swarm spatially confined. Each hypothesis offered mechanisms. Each could reproduce some subset of the observed anomalies, but none cleanly explained the entire dataset without invoking multiple free parameters or ad hoc adjustments. The exotic volatiles hypothesis struggled with the spectral stability. Volatile release should still vary with temperature, even if sublimation curves were unusual. The fractal dust hypothesis had difficulty accounting for the low gas production rates. Fractal grains still required gas drag for ejection. The plasma envelope hypothesis required ionization rates higher than typical solar ultraviolet flux could plausibly sustain at this heliocentric distance. The self-organization hypothesis lacked a clear energy source to drive patterning over the short timescales observed. The swarm hypothesis required continuous particle ejection at velocities too low for standard sublimation pressure, but too high for weak gravitational binding given the nucleus's small mass. There was no consensus. Models proliferated, each capturing part of the puzzle, but leaving gaps elsewhere. The observation that united all interpretations was this: the boundary layer around Atlas represented a regime of cometary behavior where standard assumptions were insufficient. Whether that insufficiency stemmed from unusual composition, rare but natural interaction effects, or something requiring new physical principles remained unresolved. The object's trajectory offered future opportunities for clarification. Orbital projections showed 3I Atlas would continue inward, reaching perihelion, closest approach to the Sun, in mid-2020 at roughly 2 astronomical units, just inside Mars's orbit. This was closer than the detection distance, but not dramatically so. The object would not plunge into the inner solar system like some long-period comets. Still, the increased solar flux would intensify sublimation, potentially triggering changes in the boundary layer's structure or revealing new activity. Observing campaigns were already planned, coordinating ground-based and space-based assets to capture the perihelion passage in multiple wavelengths. After perihelion, 3I Atlas would swing outward, its velocity carrying it beyond the Sun's gravitational reach and back into interstellar space. The outbound leg offered its own observational value. As solar flux decreased, would the boundary layer fade symmetrically, or would it exhibit hysteresis, lingering brightness, or structural features inconsistent with simple thermal cooling? Would the non-gravitational acceleration reverse direction as expected if driven by outgassing, or would it persist, suggesting alternative momentum sources? A close gravitational encounter with Jupiter was possible depending on final trajectory refinements. If the object passed within the giant planet's Hill sphere, Jupiter's gravity could perturb the orbit, altering the outbound trajectory and potentially extending the observation window by bending the path back toward Earth's line of sight. Such an encounter might also tidally stress the nucleus, triggering outbursts or structural changes that would provide additional diagnostic information. New instruments were coming online. The Vera Rubin Observatory, with its wide-field survey capabilities, would monitor 3I Atlas's light curve continuously. The European Space Agency's upcoming Comet Interceptor mission, though not targeted at 3I Atlas, was refining rapid response protocols that could, in principle, be adapted for future interstellar visitors. Ground-based interferometry was improving, potentially allowing direct resolution of the boundary layer's inner structure if the object's brightness cooperated. Advances in machine learning were enabling more sophisticated analysis of archival data, uncovering patterns human analysts might overlook. But these were future possibilities, contingent on funding, weather, instrument health, and the object's own behavior. What was certain was that 3I Atlas would not linger. Interstellar objects pass through quickly, their hyperbolic trajectories granting only brief windows for observation. Once gone, they do not return. The data collected during this apparition would become the permanent record, scrutinized and reanalyzed for decades as models evolved and new theories emerged. The challenge for astronomers was to resist premature conclusions. History offered cautionary tales. Oumuamua had sparked intense debate, with hypotheses ranging from hydrogen icebergs to light sails, each interpretation shaped by the limited data available and the preconceptions of the interpreters. Many claims aged poorly, as more conservative explanations gained traction. The lesson was clear. Extraordinary interpretations required extraordinary evidence, and even ordinary interpretations required humility about the limits of inference. 3I Atlas occupied a liminal space in that epistemological landscape. The boundary layer was documented, reproducible, and statistically significant. It was not an illusion. But what it represented, physically, compositionally, dynamically, remained ambiguous. The data constrained possibilities without uniquely determining them. Multiple models survived. The scientific method demanded patience, additional observations, and a willingness to revise or discard hypotheses as new evidence arrived. There was value in this uncertainty. Not every discovery yields immediate understanding. Many of astronomy's most profound insights emerged only after decades of observation, as instrumental capabilities matured and theoretical frameworks developed the language to describe what had been seen but not yet comprehended. Pulsars were detected in 1967, but not understood as rotating neutron stars until theoretical predictions caught up. Exoplanet transits were observed indirectly for years before the first confirmed detection. The physics was known, but the precision required exceeded available technology. Black holes were theorized in the early 20th century, but not directly imaged until 2019. 3I Atlas might follow a similar arc. The boundary layer might eventually be explained by refinements to cometary physics, better models of volatile transport, improved dust optics, more sophisticated plasma simulations. Or it might require new physics, phenomena unanticipated because they occur only under conditions rare in the solar system, but common in interstellar space. Or it might remain ambiguous for years, a puzzle deferred until better instruments or cleverer theorists arrive. What could not be deferred was the act of observation itself. The object was here now, crossing our small patch of space, offering a glimpse of materials and processes shaped by environments we cannot visit. Each photon captured by a telescope carried information, encoded billions of kilometers away, information about temperature, composition, motion, structure. Each spectrum, each image, each light curve data point was a piece of the narrative, incomplete alone but meaningful in aggregate. The boundary layer around 3I Atlas would continue to glow as the object approached perihelion. It would persist, or it would fade, or it would transform into something unexpected. Telescopes would watch. Data would accumulate. Models would be tested, refined, or abandoned. And slowly, with the patience that astronomy demands, the mystery would yield, or it would deepen, revealing new questions where once there had been only observation. In either case, the universe would have spoken. Our task was simply to listen.